All right, good morning. Well, thank you for being here on what may be your last class before a 5-day break. Um, it's my last class before a 5-day break. So how is everyone today? Good, good, great. Definitely ready for the break too. All right, well, glad to hear it. So yeah, a few things. So first of all, homework 8. I warned you I wasn't going to get to grading this until later on in the week, but I actually got it graded last night. And it turned out in part this was because so many people did so well on it that it was really easy to grade, right? I mean, when students' programs work, grading them is pretty easy, right? You run them, you go through some test cases, you look at the code, and if everything's great, it's 100. Um, and if programs aren't working, or if I have to, fix syntax errors in them before I can see what other parts of it do, it takes longer. And this was, the largest set of fully working programs I've ever graded in this course, which is fantastic. And it's actually a really good sign that people are understanding this stuff and able to use it. So that's really good stuff. So yeah, definitely yay all of you. All right, so grades are posted with comments, and my comments come from an automatic comment generator. So if they feel kind of terse, um, I apologize for that. But basically, my goal was to let you know where there were issues with the test cases and the code and so on and so forth. So if you have any questions or concerns about point deductions and stuff, just come by office hours or shoot me a note or something, and we can talk about it. So I had a few requests from people to see what I did for my version of this code. So I want to just show you an example of how you could do homework 8. So this was based on the way that the problem and the algorithm was presented in the write-up, and some people did things differently, which sometimes worked, sometimes didn't. But this should be very true to what was written up in the prompt and what we talked about in class. So it's fairly uninspired, right? There's nothing terribly creative in here. It's a really straightforward rendering of the steps outlined in part 3 of the prompt. So first thing, make sure your shebang is the very first line of your file and that it starts in column 1. If you put this down here, it's no longer acting like a shebang. Okay, it's just a comment. It starts with a number sign. Most comments, if they happen to have an exclamation mark after the number sign, nothing cares, right? It's just another comment. But there's this one exception. If the very first line of your file starts with a number sign, exclamation mark, then this is taken to be the program through which the contents of the file should be run if you just type the file name. So that only works if it's the first line. So don't put it down here or something else. All right, so that's got to be first. And then, a comment block with the assignment, your name, the date, etc., etc. And then here's my one sentence synopsis of what this does. 2 sentence, read standard in, cleanse the input, break into phrases, tally all the phrases, output the final tally after hitting the end of file. After, not at after. All right. So we're going to use an associative array. if you were one of the few people who did not use an associative array for this, make sure you understand associative arrays. They'll probably be on the final. They'll definitely come up in other courses, and it's a really good tool to sort of have in your bag of tools. So make sure you know how you would do this with an associative array. Okay. So when we're going to use an array, we can just start using it. But an associative array, we have to declare. So we do declare dash uppercase A, name of the array. And this I'm just putting in the very beginning. I don't want to put this inside a while loop or a for loop. I don't want to keep executing the statement. It's really a one-time declaration for the life of the script. So it says count is this thing that we can, access with keys and pull values out or put values into. So that's the declaration of my array, and it's just unimaginatively called count because it's counting how many times phrases occur. All right, so here's our main loop, while read line. That's going to wait for an input line from standard in, and then the value of what was typed in or what came in from a file will be in this variable. And this will loop until end of file, which will bring us to the end of the loop, which is right here. All right, so while read line do. So another general comment. Some people took the input from the file and strung it all together into a big, long single variable. And they made an input loop that just keeps reading a line, tacking it on to the end of a variable. Okay? Sometimes that's important. Sometimes we need to get all of the input into memory before we can start processing it. But that's inherently limited, right? If I had a few billion characters of input, that's probably going to run out of resource, right? Trying to hold all of that in memory and then manipulate it, that's going to be inefficient. So if you can process input as it's coming in, process it, throw it away, that's going to usually work better. And this was set up so that you could do that. You could read a line, process it, read another line, process it, never have to go back to that first line, right? Each line we get in, we can break into phrases, tally, and then we're done with that input line. We never need to see it again. So don't save it in memory, don't tack it onto the end of a variable, just process it, go on to your next line. Similarly, you never needed to use a temporary file in here. Okay, so some people use temporary files. You can do that, but you can also do these things in memory. And temporary files can be a little dangerous, or at least tricky, right? So for example, where are you going to open this file? You can open it in the current directory, but what if you're running this command from a directory that you don't have write access to? Right? What if you open a file and you accidentally name it something that matches a file that's already in the directory? You might clobber somebody's work. What if you open a file and the program exits partway through, the person Control-C's, and now you've got these stray files sitting in the directory, right? That might disturb somebody who's using your code. So you can throw them in the /temp directory, and you can make a file name out of some distinctive string, the process ID, the timestamp, and you can put a dot in front of it so it's hidden, right? So you can do things like that if you need to, but if you don't need to, try to avoid temporary files. It's just a little cleaner to not do that. All right. So I'm going to read a line, process it, and then be done with it. All right. So this reads the line into this variable. And then here's a little comment block. Clean up the line. So what does that mean? I'm going to convert everything to uppercase. I'm going to remove these characters. I'm going to change tabs and spaces to underscores. And then I'm going to compress strings of underscores into a single underscore. Okay, all of that happens in this one line. Okay, also changing spaces to underscores. I don't need that. That's already happening. That's already commented. All right, so how do we do that? Take your line, echo it, put it into TR to do the case conversion. And then to get rid of those characters, since I didn't want to go too overboard with escaping things instead, I changed all of these characters to an @ sign. I changed a single quote to an @ sign, and then I removed the @ sign. And then I changed spaces and tabs to underscores, and then I changed consecutive underscores to 1 underscore. Right, so this one long line does all of that stuff. All right, so now we have, a line containing possibly multiple phrases, but it's been cleansed, right? So the next thing is to break it into phrases. Well, I do that by taking each of these separators and just changing it to a space. And this is usually easier than playing around with IFS, which is why I didn't talk about that. But there's multiple ways to do this. This is a really easy way, though. Change each of these things to a space. Just did that with said. And now phrases is my cleansed conditioned input line. It's a set of phrases separated by spaces. All right. So now I have to pull out each phrase from that conditioned line. So that's the for in statement. And inside this loop, phrase will be a phrase. So all of that stuff up top is really just getting me a phrase that I want to process. And now what I'm going to do inside this loop right here is I'm going to process that phrase. All right, how do we process it? Well, got rid of leading and trailing spaces, right? Because those can be lingering even with the above cleanup. So remove leading and trailing spaces. So echo my phrase, get rid of leading underscores, trailing underscores. And then this business some people discovered, if your phrase is empty and you try to use it to index an array, you'll get a bad index error. So double check to see if the phrase is blank. And if it is, I'm just saying continue. So continue will take you to the top of your most closely contained loop. In this case, it's this for phrase in loop. So continue at this point will basically skip all of this and just go back up here and get to the next phrase from our input. All right, so if I get here, phrase is a valid phrase. So now I do my read, modify, write. So first, read the current count from the array. So that's just a straight array access. Modify it, right? So increment the count, set it equal to C plus 1, and then write it back in. So that's another array access. Just take that new value of C, store it in the count array. So that processes all the pieces of my current input line. And when I'm done, I go back up to the top, and that'll read another line from my input. So when this outer while loop is done, I've processed the entire input file. And now I'm ready to output the results. And so here we just iterate over the keys using that peculiar syntax. And before I output my phrase, I'm going to change my underscores back into spaces. So I do one more sed, change underscore to a space everywhere. Save that in a variable I called clean, and then I just output the phrase count followed by the cleaned up version of the phrase. And that's the whole program. So this was similar to what most people did, right? Some people's programs were significantly shorter. Some were longer. Either of those is perfectly fine. So any questions about homework 8? Lingering issues? If you don't have an associative array, you can always do this with parallel arrays. So you could, for example, make an array called phrases, and make an array called counts, and make an array integer called number, right? And you get your first phrase, you store it in here, you set the count to 1, you set number to 1, saying I've got one phrase stored. You get another phrase, you go through all the phrases in here to see if you find that phrase. If you don't, increment this, store your phrase there, set the count to 1. You get a third phrase, you go through your two elements in your array. So you check this phrase, does that match? No, you check this phrase, yes it does. You just increment the count. And so you know, it would be exactly the same cleansing and breaking your input into phrases and so on. But instead of just, you know, plunking it into an array using the phrase as an index, you have a list of phrases, and you just go through and check to see if it's in that list. If it's not, you add it as a new phrase and set the count to 1. But if it is in that list, meaning you've already seen it, you just increment the count associated with that phrase. So it's kind of a manually done version of an associative array. And this is a common structure. It's usually called something like parallel arrays, because this is basically, you know, a key and a value, but we're storing them in two separate arrays and just associating them. That's a reasonable way to do it, but this is this order n squared business. If you have 1,000 phrases and you get a new phrase, what do you have to do? You have to compare it to 1,000 different phrases to see if you've already seen this or not. And ballpark, you know, the next 1,000 phrases, each one's going to have to be compared to 1,000 to 2,000 phrases. That's 1,000,000 operations, right? So to process 1,000 phrases is going to take roughly 1,000,000 comparisons. And the longer your input, the slower this gets. So I had some test 4s, Wuthering Heights inputs that ran for an hour when I was testing this last night. So I had like 10 windows open at once, and I was testing 10 pieces of code by the end simultaneously, because in some cases test 4 took a really long time because of this kind of thing going on. But it works, right? It's doable. It works perfectly fine. And if you don't have, you know, a hash built into your system, or you don't want to write a hash for small amounts of data, that's a fine way to do it. The other thing some people did without using associative arrays was, you know, you can search for a phrase in a file by using grep, right? As long as you can manage the special characters, and since everything was being cleansed beforehand, you could just make a file of phrases and you can just say grep and see if your phrase is in there, right? Or you can just write all your phrases into a file, sort it, and then run unique-c, and that will go through and it will tell you how many times each phrase or each line of the file repeats the line before it. And so you can get your output like that. Now technically that should get a 0, because the assignment said you could only use awk, sed, tr, and built-in bash functions. But I let it slide because a few people did this, and it didn't explicitly say that that was forbidden, right? It said you can use awk, sed, tr, and built-in bash functions. But again, make sure that you understand the idea of an associative array, right? Because it'll come back. And so make sure you're comfortable with that. And if you're not, you know, definitely ask about it. Unique is not a built-in bash function; it's a program. Bash is you know, if and while and assignment of variables and those sorts of things. But all of these commands like awk and sed and tr and date and all this kind of stuff, these are not part of bash. These are part of Unix, right? They're programs that we can run, but they're not actually bash per se, right? But you know, arguably echo, when you say echo, there's a built-in command called echo. There's also a program called echo. So if you say, what is echo? Well, it's you know, it's a function, but it's also part of bash. So I didn't want to get too dogmatic. But in general, unique is a really good command to know, and unique-c is a nice one. All right, other questions, comments? And just as a kind of demo of this stuff in a more real world situation. So when I grade programming assignments, typically it takes me, usually they come in on a Friday. Typically it takes me about 20 hours to get through all of the assignments. So good part of 2 days working pretty solidly each day. I discovered a lot of my time is spent really just typing, and typing into Canvas in particular, which is slow and laggy and stuff. So I started typing comments into a separate file, and then when I'm done, I just go through and I copy and paste all of those into Canvas, and that actually sped things up. But I also found I was typing the same comments over and over and over again. So starting with the previous assignment, I've been giving you grading rubrics, and so I have something like this. I have a file that is sitting in front of me when I'm going through testing people's code, and next to each person's name, I just type in any issues that I see. So if your script's not named main, type in name, and if it is not executable, I type in exe, and I just put in these codes to let me know as I'm testing your program what the issues are that I encounter. And then when I'm ready to put grades into Canvas, what I do is I run a program called add comments. I give it that grading key, and it asks me what codes I want to type in. So I can say, name, 1 minor problem, 2 major problem, test 4, format, and you had underscores in your output, right? And then I go into Canvas and I Control V, and it pastes in, right, the description of what each of those codes translates to, the point value of each of those, and then the final score. And then I just grab this and I move it up to the score entry in Canvas, and I go on to the next assignment. And this is how I got through, the grading stuff in much shorter order. That and the fact that everybody did a really good job. But I'm showing you this because this add comment code is just a little script I threw together a few weeks ago, and it uses associative arrays, right? So I have this grading file that we looked at where I have some kind of mnemonic in there. So if the program's not executable, I just type exe, right? Or major minor problems with the 4 tests, or with the last test, and so on. So when I run my add comments, what does it do? It reads whatever file name I specified, which was the comment file. It makes a pair of associative arrays, one for saving point values, one for comments. And as it reads through that grading file, it uses awk to split it into 3 pieces, right? The code, or the key, the point value, and the comment. It saves those in 3 variables. And then it stores those in a pair of associative arrays. There's a points array and a comments array. And they're indexed by that mnemonic, exe, name, 1m, etc. And so it does this over the entire input file. And then it asks me for a code. I type in a set of codes separated by spaces. And then we do another for in loop. And simply go through, read the point value using that code, and read the comment using that code out of the comment array. The comments get strung together into a big long string separated by 3 tildes, and the points get subtracted from your initial grade, which is 100. And then when I'm done, I get rid of those tildes, put the grade in the beginning, and then I run that into a command called xclip, which says read standard in, put that on your clipboard. So this, took a little bit of time to write. Not too long. It was, less than an hour to put together. But now when I want to grade, right, if I have that grading rubric, I can record these short, 2 or 3 character codes instead of typing in, test case 4 had some major issues, -10, and then when I'm ready to enter into Canvas, just type in the codes, and bingo, my clipboard has what I want to paste in Canvas. Paste that, go on. So this is just an example of a case where associative arrays work really well, because the alternative would be to number these 0, 1, 2, 3, 4, 5, right? And if I had some other issue that kept coming up and I wanted to put that in the beginning, I'd have to change my numbers, or have it be out of sequence or something. So I can associate this information with this thing that I end up using as an index into an array, and that's useful. So this is just another example of this thing where once you kind of have your brain thinking about some particular thing, you start to see the world in a different way, where problems can be solved with that particular thing. And so associative arrays are that way. Awk and set are those ways. Regular expressions in general inspire that kind of thinking. So this is just in the spirit of building up a toolkit that works for you, and trying to get really good with it, right? Trying to understand really well a small kernel of things, instead of trying to understand a zillion different things without really knowing any of them really well. And someone just looked up, and Canvas does have an API. Yeah, and I've played with that a little bit. I've gone as far as with ODPs, those I run through code, and that gives me a CSV file. But I upload the CSV file by hand. But that's only a once a week kind of thing. But yeah, if I could actually upload the comments, that would be a little nicer. At some point, we run into my distrust of computers, though, which maybe comes from working with computers my whole life. But ultimately, I like actually putting in the grades myself, even if I'm pasting them. I want to put in that final score myself and see the student's name and see if there's any comments they left for me about the submission, and so on and so forth. But yeah, I might head there at some point. Thanks for the link. All right. So let's go back to talking about processes. And we started this yesterday. We were looking at the system command to execute a command in another process, right? So let's play with this thing called popen. So we talked about file I/O yesterday: fopen, fclose, fgets, and so on. That was a warm-up to be able to play with this command popen. So popen works like fopen, except instead of naming a file that we want to open to, say, write to or read from, we name a command. And that command will execute, and if we open it for writing, we will be writing into standard in of this command. And if we open it for reading, we'll be reading from standard out of that command. All right, so let's try this. So I'm just going to use P as a pointer to my pipe. And this is going to be a piped command that we're writing to. All right. So let's put some debugs in here. So we'll say we're about to call popen, and let's just call the date command. So we'll execute the command date and we'll open that pipe for reading. And let's print out the value of that file pointer that we got back. And I'll print it out as a %p because it's a pointer. So it'll format it and make it the right size. And then let's read from the pipe. That's our landscapers again. It's so weird. There's a parking lot outside my window. I don't know what the landscapers are doing, but they come around every week during section B of 224. Maybe they're trying to learn about process control. So we're gonna do the popen to open the date command, and then I'm just gonna do an fgets, and I'm gonna read up to 120 characters from that file descriptor p, right, from the pipe. And then you're going to print out the value of that string that we got back. I'm going to print it in angle brackets. And that's our whole program. All right. So let's compile this and watch what happens. All right. So we run this, and our program prints out the date and time. All right. It called popen. We got back a reasonable looking file pointer. And then it called fgets, and this was in a string variable in our C program. Okay, this is fundamentally cool. Yeah, I can just say date and I see the date. What's the big deal? The big deal is that date got loaded into this character array. All right, and then we could do whatever we wanted to. Well, we just printed it. That's not terribly exciting. That was just to see what was in there. But now we have a bona fide C string containing the date and time, and we could do stuff with that. All right, if we do this in a loop, so we'll keep looping and reading until we get end of file. Right, well, we get the same thing here because date only returns a single line of output. But we could have done something more interesting, like ps-elf. And now, you know, our program looped a whole bunch of times, and each time through, this array variable was the new value of our, you know, the next value of output from PS. I'm kind of curious what happened here. Oh. That's really bizarre. So we're only reading 120 characters at a time, and I'm thinking this line of output was way longer than 120 characters. It was MAAA followed by all of this stuff. But I have no idea what that command is. That's a really suspicious looking one. GPU preferences, yeah. Could be existential dread, definitely. Alright, so we can run Unix commands. We can run Unix commands and we can capture the output of those inside a C program. And that's potentially, you know, a useful thing to do. And when you consider that, you know, when I say Unix command, I'm also including things like bash, and we can run bash, and we can say bash-c and or sh-c and put a command in there, right? This is a lot of power that we can exert from a C program just by saying popen and then fgets. Now we can do system command, right, and that'll run a command, but if we do system ps-elf, it simply displays the result of that command on standard out. There's no way to capture it. Like this, we can actually capture that input, or that output, from the command input to us. And if we don't do this, right, our program still runs, but there's no output produced. That output is coming into the pipe, and we can do what we want with it. So let's change this PS, and let's just do a PS-LF. Let me put my print back in. Right? So, and let me make my font a little smaller. So now, we got 5 lines back from standard out of our command. So here's our bash shell, right? Here's the command p20 that got, called right here when I typed in p20. That created this process, which was sh. That's the process that ran when I said popen. And that sh, since it had a -c switch ps-lf, it created a new process to execute ps-lf. And that's the process that was running, right? You can see the state is R, which means it's running. Everything else was sleeping. That's the state that the process that was running and generating this output that we read from this fgets. All right, so that's the input side. We can also open a pipe and we can write to it. So let's open a command. Let's do good old BC and open it for writing. We don't need to keep seeing all of this stuff. So let's write to the pipe. So I'm going to do fprintf. I'm going to put in the file pointer that I'm trying to write to. And let's write 2 + 2. And then we'll say goodbye. So remember, BC is this basic calculator program. If I say 2 + 2, it should show me 4. So let's compile our program. Let's run it. And it said goodbye, and then it printed out a 4. Well, that's a little weird, because I printed to BC first, and then I said goodbye, but goodbye appeared before the result of BC happened. So let's put a sleep in here. Let's write to BC, wait a few seconds, and then say goodbye. And guess what? We don't see anything for those few seconds. And then after 5 seconds it says goodbye, and then PC shows me the output. All right, so what's going on here? This is this whole business of buffered I/O. It's this idea that when we write something to a device or a command or a file, it may not actually get written when we say printf, right, or echo, or write. There's this buffer. So here's our program. Here's the disk. And when I say put something to the disk, it actually goes into this buffer, and it will kind of hang out here until there's a bunch of stuff stored up in here, and then it'll all get written out to the disk at once. It's an efficiency consideration. And so even though at this point in my program I'm saying write, it's not actually writing out. It's hanging out in this buffered output stream. I sleep for a few seconds, it's still hanging out there, but when this program exits, it flushes out that pipeline. So what we can do is we can force this flush to happen early with an F-flush instruction. So we're basically forcing this output to get sent to the command by saying F-flush. So now we're going to do our F-flush, and then we're going to sleep 5 seconds, and then we're going to say goodbye. And this is going to act exactly the way we would have expected. It prints out, you know, the result of the BC command. We sleep for 5 seconds, and then it says goodbye. All right. So flushes are really important. The other thing we could have done was simply closed our pipe. I don't have an FP. Right? If you close your output stream, that also forces everything that's been buffered to be flushed out. But we don't necessarily want to close our output stream, but we may want our output to actually get forced to the device. So usually we use an F-flush when we want to make sure the output's been sent. And then it's good practice to do an F-close at the end of your program, or when you're done using the stream. Now when our program exits in Unix, it will close those things for us. Other operating systems, maybe not. And you can end up with you know, resource use that's not being freed at the end. All right, so let's make this a little weirder. Instead of computing 2 plus 2, let's just raise 2 to a big power. And so we'll wait a few seconds, our program exits, and then after it exited, we got all of this output. So let's get rid of the sleep. Right? So it said goodbye. And it's hanging out there, but the sleep command was still running. Right? So we hit the end of our program, but BC continues to run. So now, by not waiting for the pipe to get closed, our program has actually exited, but that BC command is still running. So if I do a ps-lf, right, there's our bash shell. And our bash shell created this shell program, 7705, which created BC, which was 7706. Well, our bash program originally created this process. So let's do this. Let's do a system call. Let's do a ps-lf. So you're going to do a ps-lf. We're going to open a BC command. We're going to send a big calculation to it. We're going to say goodbye and exit. And I'm not going to worry about warnings. All right, so what do we got here? We've got our bash program, 29263. That created a process to execute P20, right? That happened up here when I said P20. That was process 7722. 7722 is the parent of this shell command, 7723. And that shell command ran the PS command. When we executed a ps-lf after our program exited, what did we see? We've still got our bash shell. That's never going to change. This sh-c bc process 7725 is owned by process ID 1. Okay, when we said popen, we started this BC process, and this process, P20, was its parent. When P20 exited, which happened right here, this shell command for doing the BC lost its parent. It became orphaned. And so it got adopted by the init process, that's process ID 1. And it's still the parent of this BC command, so that's still out there, 7726. But this was a BC command, the shell invocation, hanging out there, and P20, its parent, was gone, right? So when we open a command using popen, and it starts executing, it's really running in its own execution thread, right? And it's got its own identity, basically. All right, so this is getting into our own existential dread now. So we can use popen to create a process, and we can write to its standard in, or we can read from its standard out. But we can't do both using popen. So we need to do something a little different. And the function we want to talk about is execl. There's a variety of functions related to this. There's execl, execlp, execv, execvpe, and so on. But they all basically do the same thing. They're a way for a process to change its essence. So let's do this. All right, so 3-line test program. We're going to print out a message which says ready to call execl. And then we're going to call execl, and we're going to say I want to run the program /bin/date. This is just the name of the program, and this is always null. And then we're going to print out a message with a typo maybe, which says done with the call to execl. All right, so we should see a print message, we should see the date, and then we should see a final print message. And I may have some compile errors in here. Nope, we're good. Okay, so you ready to see what this does? It's going to be really freaky. It says ready to call execl. It shows the date, and that's it. It worked great, except it never executed this print statement. All right, so why didn't it execute this print statement? What execl does is it basically says, change me into something else. Okay, so imagine you're walking down the street, you're wearing your clothes, you look like you've got your shoes on, and so on and so forth, and all of a sudden, you become somebody else. You look exactly the same, you're in exactly the same place on the sidewalk, but you are now somebody else. That's what this function does. It takes your current process, and at this point it says, I no longer want to be executing all of this code. I want to be executing the code contained in this file. And this function never returns, because once this is executed, this is not part of the program anymore. This is not part of the process. Your process is now running this date command. And it's fundamentally different from saying system/bin/date. Or popen/bin/date, where we get a new process. This actually changes the current process into something that is now executing an entirely different program. So a more complicated goto command that goes to other files, essentially, although it's more than just a go-to. It's more than just executing another command. It's actually becoming that command, right? And if we do a PS, you will see, right? When the PS runs, there's no P21 program running anymore. The only program that's running is PS and bash, right? So that P21 program that started right here has changed into PS. This can lead to all kinds of interesting things, but usually, the resources from the old process are cleaned up. But yeah, this is something that can get into all kinds of interesting consequences. But this is how processes come into existence, right? So fork clones a process, but unless you want a whole bunch of clones of one process running around, you've got to have a way to create different processes. So a process is cloned with fork, and then it's morphed into a different process using exec. And that's the basic strategy for process creation. So we'll play with this a little more next week. Probably on Monday we'll play around with setting up communication between processes using this. And then rest of next week we'll just kind of wrap up the course, talk a little bit about the final on the last day, and answer any questions. So have a fantastic rest of the day. Have a great break if you get a break from all of this over the next few days. Have a good one. Stay safe, and I will see you on Monday. All right, thanks.